Hello to everybody and welcome to our today's webinar. We are pleased that quite a lot of listeners from the first webinars have joined us again. And a special welcome, of course, to all those of you who are new today. Now, let me first briefly introduce our team to you. My name is Sibylle Hildner-Lippold. My profession is translator and interpreter with focus on economics. I work with the company for almost 25 years now. I'm part of the MIM sales team, and here I'm mainly responsible for our international markets like Italy and France. Dr. Johannes Maurat studied process engineering at Karlsruhe Institute of Technology. His PhD degree was in the field of feedstock development for highly porous materials. Johannes started working at MIMplus 5 years ago as R&D engineer. His main topics are feedstock development, process optimization, and recycling and production of MIM-magnets. And now it's a special pleasure for me to introduce Professor Dr. Carlo Burkhardt from the University of Pforzheim, who has joined us today as external speaker. Mr. Burkhardt is 56 years old and holds a PhD in metallurgy and materials. He has 16 years of experience as R&D director with large tier 1 automotive suppliers. From 2010 to 2016, he was CTO in our company. And since 2017, he is scientific director of the Institute for Precious and Technology Metals at Pforzheim University and professor of manufacturing technology. Now, before we start, some short general information for you. I will first briefly introduce the company to you, and then we'll go on with the lectures. Carlo will start, and then he will hand over to Johannes later on. So now, let's get started. MIMplus Technologies is an experienced and innovative manufacturer of metal parts and assemblies. And our focus is on high-tech materials. We belong to the OBE Holding Corporation with production sites in Germany and China. The company has been founded in 1904. So today, we look back at 117 years of experience in precision engineering. We have 500 employees in the world and a production floor capacity of 25,000 square meters. Now here's some key facts about MIMplus. We produce and deliver over 25 million parts and assemblies per year. Our customers come from different industries such as medical, aerospace, automotive, and luxury. We have our own tool shop in-house, and we also have our own machine construction and automation. Our research and development is equipped with a very good laboratory, and we work with a network of leading suppliers. As you can see, we hold also a lot of certificates, among them the IATF for the automotive, and we have the medical certificate in preparation, which we will pass by the end of this year. So, the topic of our today's webinar is recycling of NdFeB and production of complex new MIM-magnets. I'm handing over to Carlo now and enjoy the presentation.
Well, thank you, Sibylle, for the very nice introduction. It's a pleasure for me to talk today about the criticality of rare earth materials. First, a little overview of the University of Pforzheim, which is one of the largest universities of applied science in Germany, with about 7,000 students on a campus overlooking the city of Pforzheim. with very new buildings, and we just moved house with our institute from what you see down here to a brand new building. It is my pleasure to cover the third floor completely with our institute, which is called Institute for Precious and Technology Metals, short STI. And our institute is based really on three columns. One is the contractual research and industry support. Here we have an accredited materials lab with a wide range of different technologies, ranging from high resolution to SEM to very specialized testing methods for the local precision and also the jewelry industry. Then we have two research areas. One is the one we talk about today, which is recycling of magnetic materials based on rare earth elements. And the second, a bit smaller one, is that we look into new processes for additive manufacturing of metallic precision parts. We have 14 employees, including 4 PhD students, and we currently take part and also coordinate 2 projects. We have 5 national and 3 European research projects with a total budget of more than 26 million. And well, I'm coordinating the largest one, which is SUSMAG Pro, which is sustainable production of magnets, or sustainable magnets production, to bring it in the right order. And we are covering this subject because there's a real need to look into the recycling of rare earth materials. Because first of all, the green energy, and you know the discussions about the Green Deal we're having in Europe and about climate change, and green energy comes with a material revolution. There's a lot of talk about lightweight material, about composites, but a material that's really critical are the permanent magnets. And if you look into a wind turbine, you see in modern wind turbines, more than 2.5 tons of these magnets built into, so roughly about 650 kilograms per megawatt of force installed. If you look into mobility, in hybrid drives, you have about 1 kilogram of permanent magnets. In full electric cars, can be up to 3 kilograms, so much smaller weight, but of course, much larger quantities. And the growth rates in both areas, they're quite large. In wind turbines, currently about 16%. In electric vehicles, it's currently more than 20%. And if you look a little bit more into the newly registered electric vehicles, you see that in the last year, despite of the COVID crisis and also systems like car sharing and so on, we have a massive growth in electric vehicles, which, if you look into the development cycle, leads us to suspect that we're in a kind of introduction phase of a new technology. If you look, on the other hand, on the ratio of electric vehicle sales compared to the total vehicle sales, we see that the growth is even further, and that we are really in a growth to the maturity phase already. And when talking about rare earth materials and electric cars, we're not really talking about all rare earth materials, which is a materials group of 17 metals, which are usually found together, but we're talking about the magnet materials. And you can see this here from the blue column, that is by far the largest tonnage that's used for the magnets. And you see the second one is the catalyst, which is decreasing with a bit of phase out of internal combustion engine. So currently the magnets have a market share of around 30% of the rare earths, but this is supposed to increase very much over time. And then if we look into the applications where magnets are used today, we see that wind turbines have only 11% of share, and automotive, which means conventional cars, have 23%, and electric vehicles is a known section with only 9%. Electronic, medical, and automation being the other two very big applications, because rare earth magnets are in small motors, they are in sensors, they're in all kind of automation devices. So that adds up to a big market. And the others, the 17%, they're really toys, there are communication and so on. So electric vehicles is only a small market right now because it's an emerging market, but we can say that over 80% of all electric cars sold in 2019 used permanent magnet-based motors, so-called PMMs. And all Chinese electric vehicles use PMMs because PMMs give you a higher performance and lower weights compared with their induction competitors. So this means longer driving range, smaller batteries, so that's a big leverage that you have here. And of the 35,000 tons that we've seen, only 2,500 tons are currently going into electric vehicles. And if you look at Europe, only a quarter of it is European electric vehicles sales. So we're roughly talking about 1,000 tons. And overall, the market share in electric vehicles is around 82%, but it's expected to grow massively. And if you now look at average growth rates of 10 to 15%, you know, before I've shown you 20, this leads to enormous numbers. So that means that the increase between 20 and 30, if you assume nothing else is changing, is between 2,400 and 3,000 percentage. And assuming zero growth in all other magnets containing sectors like the wind turbines or so on, the growth rate or the demand growth of neodymium and praseodymium at rare earths is between 130 and 190% above the 2020 levels. Of course, always assume this 10 and a 15% growth. And the question is now, where is all this additional neodymium and praseodymium supply coming from? Now there are the skeptics and say this takes much longer, and some of the shortages in material supply, they will really limit the growth of the electric cars. And here I found a nice picture, which I didn't find it. I've stolen it from another presenter. It's a picture from 1900 of New York's Fifth Avenue on Easter morning, and you see there are only 2 electric cars. I marked them here with a red circle. Only 13 years later, same day, same road, situation is completely different. As I here spot the horse, the horse is apparently here. And I think if you look around, we see that the electric transversion of the cars is already happening, and we see more and more every day. And if you look then into the value chain of the electric cars, you see that only considering the rare earths elements, the value chain is a quite large one. You start with mining the rare earth elements, then you have the oxides, which you have to separate first, because usually rare earths come in a large number or in a large variety. So you don't mine one exclusively. So there's no neodymium mine or no dysprosium mine, but it's always a mixture of them. You have to separate and refine them. Then you have to make the metal. Then you have to make the alloy for the magnet, which consists of neodymium, iron, boron, and certain other alloys. Then you have to make the magnet, the component, and the OEM. And the Chinese, over the last 50 years, they have recognized that this market is important, that this is a future market. And they covered the complete value chain from the mining to the electric cars. And here, these flags, they represent really the market share. And there's another supply chain or value chain, which is a Japanese one, with some mining in Australia, with refining in Malaysia. And there's another quite diversified value chain with some mining in USA, some refining in India, and so on. And you see that there are European, or nearly European players in, with the UK making metal and alloy. Some European magnet production, mainly in Slovenia, coming out of the former Iskra in Yugoslavia. But you see that on the component side, that the US and Europe is as strong as China and Japan on the other side, in a market that is enormous, with $3.1 billion in 2080 and massively growing, as we've seen. And so this means that Europe and the US has a significant disadvantage in getting this material supply. And if you look on the left chart, you see that over the year, China has really taken over. So in the 50s, really Europe was dominating in the rare earths. Then there's from the 60s to the 80s, the US dominated the market. And then the blue one, you see that China has taken over nearly completely. And in the last couple of years, Australia, and this is the mine that is supplying the Japanese, is emerging and now coming up to quantities. But you see that we in Europe we are up here. And this is why the European Union has classified the rare earth elements. And here one distinguishes between the light, which is neodymium for the magnet, and dysprosium as a heavy, with having the highest supply risk and also having a significant economic importance, which is supposed to shift very much to the right side in the future with a European Green Deal. And this leads us to where is the material for Europe coming from? Opening mines is relatively tricky, it takes a long time because it's open pit mining, so there's a large land consumption. It's also coming with chemicals that are involved, so water has to be treated, and also radioactive material is mined with it. So opening mines is relatively complicated. And recycling, on the other hand, of the material that's already in the market is a must. Other technology methods like silver, like platinum, palladium that are in catalysts have recycling rates of 30%. And neodymium has only a very little recycling rate of around 1%. This, of course, has a reason, because end-of-life magnets, which I shortened here with EOL, these end-of-life magnets come in a wide variety. So there's samarium, cobalt, ferrites, neodymium, iron boron in the market. They're all silvery and shiny. If it comes down to neodymium, iron boron, there's sintered bonds, which are good to recycle. Polymer bonded are not, but on the outside, you don't see what's in. Then there are different protection coatings, which we will see later on when Johannes is presenting. They're complicating our life, and there's also a different state of corrosion. Then on the market side, we have to state that the take-back schemes are not sufficient, and also the overall will to recycle is not sufficient. And this leads to a situation where a large fraction of our magnet-containing waste is still exported to third countries like Africa. Another issue that the magnet content in the products is often low. For example, in the conventional car we've seen before, there's a certain amount of magnets in, but it's dispersed all over the car, coming up to 200 magnets for your window lifters, for adjusting the light, for adjusting the seats, and so the collection is very difficult. And here, if you look into a cell phone, which costed originally 1,000 euro, the material value of the critical material is just 2 euros. Of which 180 is gold and only 20% or 20 cent is the rest of it. So recycling methods, on the other hand, do exist, but upscaling of these is expensive. And for the stakeholders currently, there's a large risk in, because we don't know how the market that is dominated by China and also how the prices are developing. So this is why our largest project, as I said, is coming into play, SASMEC Pro, which is a industrialization project. So it's not research, but it's developing and demonstrating in pilot plants that a clean and sustainable recycling of magnets is possible. The project is currently the largest European project on recycling, and it's covering the whole value chain, from the recycler like Stina to the end user like ZF for the electric cars, or like Grundfos for heating pumps. The total budget is around 15 million, and as the industrial partners have to bring a certain own share in the funding that we get from the European Commission is roughly 13 million. So what do we do in a project? First of all, we're identifying applications that contain neodymium iron boron magnets, and we develop methods to separate these components from the waste stream. This is mainly automation. So with sensors, we check where are the magnets, how strong are they, because the neodymium iron boron magnets are the strongest ones. So they're fairly easy to separate. And then we're building automation to really take them out of the waste stream and to cut off the magnets. Once we cut off the magnets, we have to remove them from houses, glues, mechanical fixtures, and so on, which can be easy in some cases, very complicated in others. Then the magnets are recycled, and here we're using the IP-protected HPMS short cycle recycling, because that's environmentally friendly, much friendlier than all the other routes, and also has much less toxicity. And this means we can really do an energy efficient recycling, which allows it to be fairly cost effective. And then recycled materials are reprocessed into new magnets by 4 different manufacturing routes. So where are we standing? Currently, we looked at over 80, nearly 100 different applications, and we really disassemble everything we can get our fingers on, which can be audio modules from mobile phones up to traction motors, or what you see here is a steering column servo steering motor. Then we classify them for accessibility, for fixation and contaminations. A simple example, the steering column motor has a material value of 14 euros of rare earths, but takes 1 hour to access, which is roughly 40 euros, which leads us to assume that currently this is not a resource that can be commercially recycled. If you look at fixations and contaminations, for example, wind turbines are a perfect source because there's a lot of magnets at one place. But in this case, the magnets are housed in a stainless steel casing and they're glued in with a glue which decomposes when you thermally demagnetize the magnet and leads to massive contamination. Or here you see the traction motors where the magnets which you see here are fairly difficult to access or to separate. And the second parameter then, of course, that we look at once we extracted the magnet are the magnetic properties, the microstructures, coatings, and chemical compositions, and so on. This is all fed into a comprehensive database where we can access all the data, and it also helps us to establish recycling factors and a labeling system, which is important also to give the OEMs later on a hint how to better design their magnets for recycling. Then the recycling itself is a fantastically simple process because neodymium iron boron is very reactive to hydrogen. So what happens if we introduce hydrogen into the magnetic structure? You have the hard magnetic phase, which is the light orange part. This remains fairly unaffected by the hydrogen, whereas this grain boundary phase, takes in the hydrogen, forms the hydride, and this hydride is bigger in volume. And as in winter, when you have water that is freezing and expanding the volume, is making a crack in the road. Here, this expanding of the volume leads to decomposed powder into the magnet into a friable non-magnetic powder. And what you've seen here on the video, which I started again with a hard disk drive magnet, that the corrosion protection coating that's on top is flaking off in large flakes and can ideally be sieved off. And so compared to the primary production, which goes from the mining of a solvent extraction and refining to the alloy and the magnet production, and then the component, and also compared to conventional recycling, where you go via hydrometallurgy back to the neodymium or the dysprosium, and then go through refining and the alloy production, the magnets production again. Our route with the hydrogen allows us to do a short loop recycling because we keep the alloy as a magnet, as a powder, which allows us to make sintered or polymer bonded magnets, or what we talk about today, Johannes is talking about today, metal injection molding. If the contaminations are too large, we can recast this material, take off the contaminations as a slag, add some new alloying elements, and then come up again with a high quality material. But what we focus on today is metal injection molding, which is done by our project partner, MIMplus. And so I'm happy to hand over to Johannes, who will explain to you that process in detail. Thank you very much.
So thank you, Carlo, for the nice introduction and your presentation about the criticality of rare earth elements and presentation of the SUSMAG Pro project. My topic of my presentation today will be how to recycle neodymium iron boron magnets and the production of complex MIM-magnets with the metal injection molding process. I will start first with a short overview about the properties of neodymium iron boron, which is the strongest magnetic material that is known so far, for the strongest permanent magnets that are available so far. Permanent magnetic materials have been developed since the last 100 years. A lot of different alloys But the neodymium iron boron has the strongest energy product of all developed materials so far, even if it's only roughly 30 years old, the alloy. If you compare the size of a magnet, you see a neodymium iron boron magnet, it's only 1/10 of the size of a ferrite magnet and roughly 1/5 of alnico, and also much smaller than samarium cobalt, which is also quite a commonly used permanent magnet alloy. Neodymium iron boron magnets are produced in two main state-of-the-art processes, which is the pressing and sintering of larger blocks for production, the strongest magnets with the highest energy product that is available for the permanent magnets. But the problem is sintered magnets, conventional press and sintered magnets, can be produced only larger blocks, which are not very complex. And if you want to produce more complex magnets, you need cost-intensive machining like EDM or grinding to realize magnet shapes like this arc, this rings, or other complex, let's say, quite simple geometries. The second state-of-the-art process to produce neodymium iron boron magnets is the polymer bonded route, where you disperse permanent magnetic powder into polymer, and then you use a shaping process like injection molding or extrusion to shape these polymer bonded magnets with a higher complexity. You can also produce multipole magnets, but the energy product is quite weak. Now we come into the game with the metal injection molding process. The metal injection molding process uses the concept to combine the sintered magnet route with the polymer bonded magnet route to produce sintered magnets with a complexity that's only known so far from bonded magnets. It means the energy product is the same as for sintered magnets. The magnetic properties are the same as for sintered magnets, but the complexity is much, much higher. And also the orientation of the magnets can be realized in a higher freedom. To summarize that again, on the next slide, you have here the sintered magnets, low complexity, but very high energy product, and only a simple magnetization. The bonded magnets you can produce in a high complexity. You can realize complex magnetization, multipole magnets, but the magnets have a low energy product. And in the MIM magnets, which are sintered magnets, but shaped with a bonding technology, in the liquid phase, you have a high complexity, high energy product, and you can realize a complex magnetization. Our vision we have is to introduce that MIM process into a closed loop recycling process. At the moment we are starting with the virgin material or end-of-life magnets. You can produce the powder, the magnet powder, use the MIM process to produce complex shaped magnets, use it, and we see in our vision that in the next 5 to 10 years, the end-of-life magnets will come back, and then we have the closed loop process. We know at the moment there's no working collection process within Europe, but as Carlo mentioned in his presentation, there's a high demand that we will develop that, and we are honored to develop that within Europe during the next years. At MIMplus, we focus due to the funding of several European R&D projects during the last years. We focused on production of complex shaped neodymium iron boron magnets with the metal injection molding process. With help of all these processes, we build up the whole process chain in-house. We can produce MIM magnets from virgin material, but we also have the closed loop recycling process to produce MIM magnets with similar performance as the end-of-life magnets in-house with our process chain. As Carlo mentioned, we are part of the SUSMAC project, and we built up a recycling and reprocessing pilot plant at MIMplus. I'd like to introduce the metal injection molding process to you generally first. That means for a lot of different materials, for stainless steel, titanium, but also for neodymium iron boron. And I will explain it in more detail based on the neodymium iron boron on my next slides. First, the MIM, it's a powder-based process. You have metal powder that is mixed with polymer mixture at elevated temperature to make the so-called feedstock. It's just a mixture of the metal powder, which is dispersed in the feedstock, and then you get pellets that can fed directly into injection molding machines, then can be shaped with conventional injection molding machines that are known from the plastics industry. Then you get the complex shaped cream body, which still consists of 80 to 90% of metal powder and 10 to 20% of binders. These binders are first partially removed by the debinding process, and then only 1/3 of the binder is still in the part. Then the thermal debinding and sintering process follows, where the residual backbone binder, which is still in the part, is decomposed completely, and then in the sintering, the open porous structure is transferred into 100% metallic part. There are no organic carbon anymore in the part, and it's nearly 100% dense. It means we have a density of larger than 96% in general. At the first glance, this process can be quite easily transferred onto neodymium iron boron, but in reality, it's quite similar. It's quite challenging because the property of neodymium iron boron is highly pyrophoric if you use small powder. So it starts to burn, it starts to glow at room temperature. If you don't protect it, for example, with inert gases or appropriate containment systems. And that reactivity of the powder with oxygen, nitrogen, also carbon, makes the MIM process quite critical for working with that powder. Because MIM is a binder-based technology, so we use organic binders. These organic binders easily react with the neodymium, and that make it quite complex, as you will see on the next slides. Furthermore, neodymium iron boron alloys often contain hazardous elements like cobalt. So you need special process equipment, special process know-how to work with that reactive and sensitive product to handle it. That leads to challenging steps over the whole process chain, starting from the powder because it's highly reactive, coming to the compounding where you still have to work with the highly reactive powder. Then the injection molding, which is a bit special for neodymium iron boron magnets because you need an alignment system for the magnetic alignment of the part during injection molding. The debinding, it's not so complex, and then the thermal debinding and sintering step follows, which is a really critical step because you have to prevent that a powder doesn't react with the light elements like carbon or oxygen. And then in the end, you have the finished part. I didn't mark it as critical, but in the end, it is because you have to protect even the sintered magnets by corrosion protection coatings, because if you do not, they will corrode quite easily and fast. I'd like to start first with the powder production. We start, for example, with end-of-life magnets. You have to extract the end-of-life magnets, for example, by stamping these out of electric motors or by shredding, for example, smaller assemblies to extract the magnets out of it. Then they transferred into a HPMS reactor where the so-called HPMS reaction follows, as Carlo introduced earlier, and I will show you on the next slide again. And then you get the clean NdFeB powder. A second approach is to use virgin material where you directly feed the virgin material into the reactor, the hydrogen decrypitation reactor, and you get also clean, fine neodymium iron boron powder. The recycling route, it is, as Carlo showed, you introduce a permanent magnet into hydrogen atmosphere, then the whole magnetic microstructure falls apart, and you only have to guarantee to collect the powder and to separate it from the coatings or other residuals like organic carbons, glues, resins, and so on that could be on top of the magnets. And the clean powder can be directly used for the MIM process. If you use virgin material, you have two sources. First could be ingots. It's just molten material cast into blocks, or you can use strip cast material, which is rapidly quenched molten neodymium iron boron alloy. You get it in small flakes, and this can be fed into the HD reactor in the hydrogen degradation reactor. Then you get the powder which has to be processed, for example, by milling, as it is state of the art for pressed and sintered magnets. The powder can then be used to produce the so-called feedstock. Therefore, we take the metal powder, mix it with suitable organic components, mix it at elevated temperature, and disperse it in a compounding machine. And then you get a good homogeneous mixture, and then the pelletizing step can follow, and you get a feedstock which looks like that. In the feedstock, the polymers protect the powder, and it is quite comparable to state-of-the-art MIM feedstocks. But critical here is to use appropriate binders and appropriate technologies to mix the powder with the polymers without reaction of the powder with the carbon or the oxygen, because it has a direct impact on the remnants and the coercivity of the sintered permanent magnets. After production of the feedstock, the injection molding step follows, which is well comparable to conventional MIM, conventional injection molding. You can use conventional commercial injection molding machines, but the specialty is in the MIM molds that are used. We produce them in-house at MIMplus. We developed the know-how to produce these because you have to integrate a permanent magnetic field, into the mold to allow for alignment of the particles in the magnetic field to produce magnets with the highest performance, which are anisotropic magnets. If you have to closer look onto a tool and onto the feedstock, you can imagine that every single powder particle shown here behaves like a single magnet. And if you put a magnetic field onto that feedstock, you get an alignment of the particles, and the particles are pre-aligned in the feedstock. The feedstock solidifies, and the pre-alignment is stable in the produced green part. And then you can produce so-called anisotropic magnets. This pre-alignment stays stable until you reach the sintered magnet in the end. A second point, which is quite interesting in the alignment and which is innovative for production of MIM-magnets, is that we can realize multipole magnets like geometrical radial magnets during injection molding. Even Hilbert arrays can be produced. Here shown two examples of a multipole magnet. We see here the green part shown with a magnetic flux foil. You see here one pole, here the second pole. Here it's 4 pole magnets, 1, 2, 3, 4 different poles. And on the side, you see also the magnetic poles here of the produced green part. After production of the green part, the so-called pre-debinding fellows, which is well comparable to conventional metal injection molding. You can use, for example, organic solvents that allow extraction of the binder without reaction with the powder. The extraction of the binder means here to remove 2/3 of the organic binder, which is in the feedstock. And then what will be left, as is shown here in the capillary bridges between the particles, is the so-called backbone binder, which leads that the debinded parts are still stable and can be transferred easily to the next step, the thermally binding and sintering, without letting the parts fall apart. The thermally binding sintering step is one of the main critical steps in the whole process chain, because you decompose here the remaining backbone binder in the open porous structure. And there you need adequate thermally binding procedures to guarantee that you don't have any reaction with the decomposition products with the highly reactive neodymium iron boron powder. And then after you deal with that, the sintering step follows, which is the densification of the porous structure to a 100% metallic and dense permanent magnet. After the sintering step, you take the parts out of the furnace and they are non-magnetic. Then you can post-process them, for example, with machining if you need. But the advantage of MIM is that you don't need that, because we have a high complexity And then the magnets can be directly pulse magnetized to make them to permanent magnets, or they can be coated with several state-of-the-art coating systems that are also state-of-the-art for sintered magnets that are on the market since several years. Typical coatings are, for example, nickel, copper, nickel, or also tin nickel or nickel, copper, nickel, and gold, which we developed in-house at the OBE Group. And we also have several sub-suppliers with which we work together to coat our recycled and virgin MIM magnets. Now I'd like to continue with several case studies to show you where the metal injection molding route can be applied on. I would start with the recycling process of out-of-specification magnets. We received these magnets from a magnet assembly producer. The magnetic components haven't been in the range where he wanted to have them. Then we took the magnets, treated them with the HPMS process, have chosen an appropriate strategy for removal of the coating, which was here nickel, copper, nickel, and we just sieved the nickel, copper, nickel flakes off. Then we developed a feedstock to injection molded parts, and then the thermally binding sintering and annealing process was adapted onto that composition of the powder. If you have a look on the magnetic properties of the MIM magnets, the whole process was quite successful. You see here the starting grade was the N33SH. The blue line is the hysteresis curve of the part, and the red line is the properties we reached with the MIM parts. So we can say we can reach, in this case, a remanence of 95% of the raw material and coercivity of 91% of the raw material. And the microstructure of the MIM magnets is well comparable to that of the end-of-life magnet, the present sintered magnet, because we have sintered magnets but shaped in a more complex way. For our customer, this was quite sufficient because he wanted just to have the selling criteria of 100% permanent magnets, recycled permanent magnets he wants to have in his product. And you see here, it is reached easily. Second case study I'd like to show you is recycling of end-of-life magnets, where the magnets were received from scrap dealer. These were wind turbine magnets, thermally demagnetized, and the magnets were processed to powder and then were used in the whole MIM process to produce MIM magnets. And for that case, it's the N38H alloy. We were successful to reproduce the remanence to 100%. It was here 1.18 Tesla, while the optimization on coercivity is still ongoing, which is more an annealing and thermal treatment process here. A further case study is a magnet, a very thin magnet for electronic devices. Our customer wanted that we work with 100% virgin material. He doesn't want that we work with recycling material at the moment. The magnet will come into very compact magnet assembly that needs magnets with a high performance, but with a thickness of below 1 millimeter. That is quite critical if you look on the conventional production processes, because there you produce larger blocks and then cut them via wire cutting, and then these thin magnets are quite fragile, and you have a lot of scrap that you get during wire cutting. So the yield was quite low. With our MIM process, we realized to produce the parts with one shot without any post-processing. A further case study is about a design. It's a holding magnet. We already had in production at MIMplus. We produced a holding magnet for the furniture industry, which consisted of 3 different parts, 2 soft magnetic parts and one rectangular shaped magnet. All these 3 parts were glued together into a plastic tube, and that was quite cost intensive here because we had to deal with 3 different tiny parts. And then we designed together with our customer a new MIM-magnet with a clip feature that was directly integrated into the magnet. And then it was possible to take the MIM-magnet and just clip them into the plastic tube. And we don't have the cost-intensive assembly and gluing steps we had before. And that design you cannot produce with state-of-the-art technologies so far. It's only possible by hand. The last case study I'd like to present to you is MIM-magnets for the e-mobility. Nearly all motor designers think in simple shaped block magnets for permanent magnet motors. And they think that the rectangular shape of magnets is fixed. Typical challenges in the electric motors are solved with design changes on other motor components, like the soft magnetic electric sheets, like the power electronic and control system, or they change the motor design and the arrangement of the magnets, but which are all the time rectangular block-shaped magnets. With our MIM technology, we allow for large-scale production of completely new magnet designs with so far unreached potential for motor performance. I have here one example out of the literature. It is a simulation of some researchers that wanted to reduce the torque ripple effect in electric motors. They said, okay, how should the magnet shape look like if we want to minimize torque rippling? They got to this quite special freeform shape. They said, okay, nobody can produce that so far. How can we make it that it's at least can be a bit produced by pressing and sintering, and they got to that shape. But it's impossible to produce that in larger scale with pressing and sintering. But these geometries could be ideal for the metal injection molding technology. And with these optimization, you see here, it's a green yellowish line. It's the torque rippling at the beginning of iteration 0. And these blackish lines are nearly without torque rippling after optimization of the shape. I'd like to summarize my presentation today with a summary. I introduced the innovative MIM technology for production of neodymium iron boron magnets for the production of permanent magnets and geometries that haven't been economically before. We can produce MIM magnets in a high freedom of design with magnetic properties that are equivalent to state-of-the-art sintered magnets. We don't have any limitation on the magnetic rate and on the chemical composition. At MIMplus, we build up a closed loop recycling process for production MIM magnets from recycled material and also from virgin material. This new innovative MIM technology for neodymium iron boron allows unique chances for all sectors, starting from the automotive industry, medical industry, aerospace, electronics, and consumer industry. Thank you.
Well, thanks for your interest, dear listeners, and thanks to Carlo and Johannes for this very interesting presentation. You can here see an overview of our webinars, which we have presented to you this year. And for all those of you who have missed the first 3 webinars now, you can still stream them from our homepage, or you can watch the YouTube video. Of course, also this present webinar can be downloaded from our homepage shortly, and there will be a video in the YouTube channel. In case you have any questions or you would like to get in contact with us, or if you need to know something more in detail or would like to give us a general feedback to this webinar, please send all your questions and comments to info.mim@mimplus.de. And we are looking forward to welcoming you again next year, because also in 2022, our webinar series will be continued. So have a nice time until then, and goodbye.
Bye.
Thank you.
Thank you.